everyone. I am Parashmita Biswal, lecturer in Metallurgy Engineering at UGA Raurkela. So today I am here to discuss a topic that is critical dissolved shear stress. So whenever we talk about sleep, there are many factors on which sleep depends. So basically, when we apply an external load, then only sleep occurs. So that external load must be higher than the internal energy of that particular sample or that particular material. So here three different things are written, like the first one is magnitude of the shearing stress produced by external load. So whatever load we are applying, how much magnitude of stress is occurring on that sample, that is very important. So second one is the geometry of the crystal structure. Sleep happens, whenever happens, it always depends on the crystal structure and the orientation of the sample. So third one is the orientation of the active sleep plane with respect to shearing stress. So we are applying some external load on some particular sleep plane, which will be called preferred sleep plane, and it is easier on that preferred sleep plane to the sleep to happen. So basically there are preferred sleep plane differently for BCC crystal structure, FCC crystal structure, and for HCB hexagonal closed pack structure. So let us discuss what is exactly critical dissolved shear stress. So what happens, there is some minimum energy level or some threshold energy which we need to exceed in order to cause some sleep. So here I will be writing some. Threshold must be less than some external load. Whenever this thing happens, then only sleep occurs. As it is written here, the threshold energy, that is the internal energy of that particular material, single crystal, and the EL is the external load which is applied from the external side so that the sleep can happen smoothly. So in a single crystal having different orientation at different direction, different type of stresses are required to cause the sleep. So in order to resolve that, this concept CRSS, critical resolved shear stress, come into action. This is first recognized by scientists skimmed, and this is the solution of applying different stresses at different orientation to cause sleep. So to calculate critical resolved shear stress from a single crystal, we will assuming a cylindrical body where P is the load applying from the top and applying from the bottom, A is the area of cross section, N is the, there will be a sleep plane we will be choosing, here it is shown, N is the normal or 90-degree angle normal drawn to the sleep plane, this one is the center 0. So, and this tau r is the sleep direction on which the sleep probably taking place. So, as it is P is the angular at an angle to the origin and normal is 90-degree to the sleep plane. So, there will be an angle between this load and this normal. Similarly, there will be an angle between this load and this sleep direction. So the angle which will be forming between load and normal, that will be called phi, and lambda will be the angle between the external load applied on the cylindrical body and the sleep direction. As it is shown in the diagram, here the A is the area of cross section, N is the normal to the sleep plane, and tau r is the sleep direction, where P is the external load applied on the top and bottom of the body. So suppose here forming a triangle, and if I am find out find out the cos phi, that will be the area divided by, suppose this is the origin, the so the angle on which this plane will be inclined, that will be, suppose the portion of slip plane on which this will be inclined, that will be OM. It means A divided by cos phi is the section of slip plane. So here is the slip plane. Similarly, here lambda is the angle between the load and the slip direction. So if we talk about the area slip plane on which angle phi will be lie, that will be A by cos phi, and the component of the axial load acting in the slip plane, that will be cos lambda divided by portion of slip direction divided by P. So the axial load direction equals to P cos lambda. So similarly, here it is written that A cos phi will be the slip plane inclined at an angle, and the axial load, that is P cos lambda, which we have found out from here and here. So last video, as we found out the slip plane that will be inclined at an angle A by cos phi, and the axial load that is acting on the slip plane in slip direction, that will be P cos lambda. So if we will find out the CRSS or the tau r, that will be the load by the area. So P cos lambda divided by A divided by cos phi. So ultimately P divided by A into cos phi cos lambda will be the formula of tau r or CRSS. So we will be seen here, as this is the formula and two cos angles are there, cos phi and cos lambda. So if cos 45, cos phi will be 45 and cos lambda will be cos 45. In both the cases, if the angle will be 45 degree to each other, then the shear stress will be maximum, because the value will be P by A. The value will be P by A into 1 by 2, and this is the maximum value. If in any case, if one of the angle will be 0, either cos phi or cos lambda, one of the angle will be 0 or 90, if one of the angle will be 90 degree, it means cos 90 degree will be 0. So ultimately CRSS value tau r will be 0, and that will be the minimum value 0. So maximum is tau r 1 by 2 P by A, and the minimum one is 0, CRSS 0. Slip will not occur for the extreme orientation, since there is no shear stress on the slip plane. So whenever one of the angle will be 90 degree, there will be no shear stress, because the CRSS value will be 0, so no slip will be occurring. And this is the maximum in case of tau r equals to 1 by 2 P by A. That is the maximum value where more number of slips can be happen easily and smoothly. So crystal close to the orientation tend to fracture rather than slip, because there will be no slip occur. So there will be ultimately the brittleness will hike, and it will prefer to get fracture rather than slip. Thank you.